vein to return it back to the heart. And so this is your capillaries, and then there's your artery, and then there's your vein. And we discussed that. So you understand that the pressure here pushes the fluid out, and then the proteins here suck it back in. The pressure will push it out, the proteins will suck it back in, right? And the openings here in the capillaries, normally, if you're normal, the openings here shouldn't be that big as to allow your formed elements and your major proteins, right? RBC, WBC, platelets, albumin, globulin, fibrinogen, they shouldn't be able to escape your capillary network. The albumin is the key to suck it back in, right? But like I said, when we study the cardiovascular system, we're looking at it just as something that still pictures of the cardiovascular system. In reality, the bus keeps moving. It just keeps moving, and there's always the leftover fluid. So the function of the lymphatic system, you have the lymphatic veins that pick up and return. And you understand why we return it to the vein and not to an artery, okay? It's something to do with pressure. If there's high pressure, it will resist anything you return there. And so that's why it makes sense that the lymphatic system drains into a vein, the right side of the heart, okay? And you understand why we don't have lymphatic arteries. We have only lymphatic capillaries, lymphatic and lymphatic veins. And by looking at the lymphatic capillaries, you see how the capillaries are anatomically, they're wider spaced. They're leakier than they are leakier than the blood capillaries. Okay? Right here. They have to allow. They have to be widely spaced so that they can allow even maybe leftover proteins. That's the job of the capillaries. Now, the lymphatic capillaries, if you recall your cardiovascular system, the cardiovascular system being a closed circuit right here, because the cardiovascular system is a closed circuit, you see, at least there's pressure, right? It's just closed. So what I'm trying to drive at is these capillaries, they have no danger of being collapsed, closed. It's just one, it's a closed circuit. So there's no point that it can be closed. The capillaries, the blood capillaries. The lymphatic capillaries, it's a different story. It's there's nothing, it's not a continuous cord, right? Over here, it's open-ended. It's not a continuous cord. So there's a possibility for your lymphatic capillaries to collapse. Does it make sense? Compared to your cardiovascular system, see? The capillaries, there's nothing, you can't collapse the capillaries, but this one, very easy to collapse. That's why you need to remember those anchoring filaments. That's the purpose of these anchoring filaments, to prevent your lymphatic capillaries from collapsing. It's an open-ended thing. So it's very easy to be squeezed shut if there's a lot of interstitial fluid here, like interstitial edema, right? But these anchoring filaments, which is connective tissue, it prevents that from happening. It will keep it open, and that's what you want. You want to keep it open so that the fluid can enter here, okay? But because they're leaky, we said that even your bacteria can enter, germs can enter, toxic substances can enter, cancer can enter. anything can enter. That's why we have those lymph nodes. And you should understand the difference between your lymph node and your spleen, right? And lymphatic tissue. So that brings us to the next topic, which is immunity. We looked at this first line of defense. We look at now, how are we able to defend ourselves? Now we see that we are really uh, open. There, we are open to any kind of infection. We're prone to being invaded by enemy forces. You understand the difference between antigen and pathogen, right? We we studied that. So we looked at this first line of defense. So anything, your intact wrapper and the secretions from that wrapper makes up your first line of defense. You know what I mean by wrapper, right? Your skin, your epithelium, your lining. Then, what if there's a breach? Let's say you had a boo-boo. Now comes your second line of defense. The second line of defense are your, I call this your, like, non-special, in the army you have the special forces. They're supposed to be the elite group. This is your special forces. So your non-special forces are this one. You have your neutrophils. These are your white blood cells that you already studied, right? So they have the property of phagocytosis. They're able to do that. And that's where your white blood cells are, right? They form part of your lymphatic tissue, right here. See? That's where your white blood cells are. So if there's a breach of your first line of defense, the antigens, right here, they will meet with your second line of defense right here, which are your phagocytic cells. They are white blood cells. And what they do is they try to neutralize it by phagocytosis. Okay? So these are cells that have that phagocytic property. Can you see? Is it too bright? Oh, don't forget.
Oh, yeah.
Okay. So, can you see, or is it?
No, that's good.
It's good?
It's good.
Okay. So you see this monocyte, dendritic cell. Do you remember this one? This is one cell that you find in your skin and your nervous system. The neutrophils, basophils, they have that property. They're able to protect us through phagocytosis. That's their common uh, common activity that they do to protect us. And so they're here. They form part of what you call the lymphatic tissue. Okay? So again, right here, you see, if there's a breach, you have your lymphatic tissue. What do they do? Phagocytosis. So that's your second line of defense. That's no longer the lining. So they form your second line of defense. You understand? Okay? In addition to cells, we also have chemicals that help us with your second line of defense. Okay? We have these proteins called interferon. Interferon.
Part of that slide's missing.
This is missing.
It's too big.
Oh. Okay. It's not.
Mm-hmm. There we go.
Okay. Okay. So you have your interference. What is an interferon? This is how they do it. So cells that are infected. So this is your host cell. This is your own cell that has been infected, let's say, by a virus. So this cell is already infected, but at least it can send messages to the neighboring healthy cells to protect them. And that's what interferon does. See? Interferons are released by the virus infected cells And it's like the interference serves like the message. You know how they talk to one another? So an infected cell talks to a healthy cell through an interferon, warning them. That's how they talk. Do you understand? So this is the infected cell. See, the virus infected it. And this infected cell will try to protect the other healthy cells by making an interferon or interferons. So think interfere with infection. So it's like you're sacrificing. I'm already sick, but at least I want you to know that there's this virus going on. You need to do something. So you're trying to give the information to the neighboring host cell. When the neighboring host cell sees that, it can try to make antiviral proteins. Proteins to protect itself from, it will form a shield so that even though there's the virus still present there, you're able to uh, prevent the spread of that virus because of the sacrifice of the sick cells in your body. Does it make sense? So you have different types of interference. You see this alpha and beta to inhibit virus. So for bacteria, the gamma I'm sure you've heard of this one, gamma injection of interferon, the alpha and beta. So this is for virus. If you're sick with the virus, people with like leukemia or immunocompromised individuals. So if you have, let's say, cancer, if you're immunocompromised, maybe you're not able to do this one. So what you will get is a synthetic injection of this one. And what it will do, it will at least try to save your normal cells. You understand this picture, this slide? Okay? So interfere is another protein. Interfere, just say it. Think interfere. This is able to, what makes the interference? The infected cell. Okay? Another type of second line of defense. So what are these? These are present in your body. Next, you have the complement system. So think of this as like your clotting mechanism, the coagulation pathway. You know when we discussed, I said in our blood we always have those clotting proteins, but they're in active form, remember? And then it's a cascade, or if there's tissue damage, you activate one of those clotting proteins, factor 8, then you activate, which is the end is factor 10 activation, which converts prothrombin to thrombin, remember that? This is the same thing. In our blood, what part of the blood? The plasma, always, okay? In our plasma, we always have these proteins. They are called complement proteins. They are proteins, they are not cells. Okay? And in case there's pathogens in your blood that entered, the complement proteins, see, it's a cascade. So C3 becomes active. You don't need to worry about these names too much for you guys to remember. Do you understand? You have these proteins always in your body, okay? In your plasma. They are in inactive form. They just are there. And when there's a possible anything foreign, they get activated. It's a cascade, you see? C3 gets activated, activating your C5, you see? And then C5 activates this. And look at the end result. The end result of activating your complement proteins is formation of what we call a membrane attack complex. Membrane attack complex. They aggregate and form like a pin or a thumbtack where they pierce the cell. This is a cell membrane. They pierce the cell membrane of a bacteria or maybe an infected cell. So when they pierce that, don't you think cytolysis will happen? Which means this cell will die. If this was a bacteria, it will die. You see? You have this always in your body. So your infected cells, they secrete chemicals. And these chemicals will activate this one. Result, this one. Another result of activation of your complement pathway is inflammation. It leads to inflammation. And we know that when there's inflammation, right, there's swelling, you call on your white blood cells. So your while your proteins, while this complement is trying to attack, I don't want to use the word attack because you may think that these are cells, these are just proteins, okay? While they're piercing the cell membrane of the infected cell or the pathogen, they're also triggering inflammation, which is what will cause the actual white blood cells to try and do their job. They're the ones that are able to do phagocytosis, remember? The respiratory burst, okay? That's where you end up with the pus. And another very important effect of complement protein activation is what you call opsonization. Opsonization. Okay? I'm going to tell you. Coating. Opsonization means coating. Coating of the pathogen. You know, just like my mother, who eats toast? Do you eat toast? Do you like to put butter on your toast? Toast, it tastes much better when you put butter on it, right? Than plain toast. That's the same, the basic analogy or same analogy with toast, not toast, with foreign substances. Sometimes, or the purpose of opsonization is to coat your pathogen, to coat your antigen, I'm sorry, or pathogen, to make it more appealing to your white blood cells. So it makes it, the book by Hall's Anatomy and Physiology, I always love it. It says there, to make it tastier for the phagocytes. And then they're enjoying their appetite. So they have an increased appetite, they do their phagocytosis. See, this is a white blood cell. This is a phagocyte. See how it's enjoying it? It's enjoying its meal. Whereas if it wasn't coated with these complement proteins, maybe it's not going to be as appealing to your white blood cells. Okay? So that's what the complement system does. When do the complement system get activated? When there's an invading antigen or pathogen. So they get denatured, right? They're nothing but proteins. They get denatured, which is like a cascade. The next one gets denatured, then the next, then the next. Before you know it, you're forming a membrane attack complex. You're also calling on your rest of the white blood cells by inflammation. And then they're also coating the bacteria to make it appealing for your phagocytes to do their phagocytosis. You understand that that opsonization? Okay, that's opsonization. Opsonization is also very important. By opsonization, the white blood cells are able to present their, we're going to talk about this in a minute. I want to go to the next one first. Another very important second line of defense is called fever. We know that fever is helpful, right? Because what does fever do? So how do you get a fever anyway? You see, the pathogens, when there is any kind of infection, it will cause as the phagocytes are trying to neutralize the infection, they are also releasing this interleukin. These are nothing, just think about your cells as talking to one another. That's how we talk to. If I want to tell you something, I have to open my mouth and say it to you, right? So that's the same thing with your cells in your body. They talk. It's either, if it's nerve cells, they talk by releasing neurotransmitters. Your endocrine glands, they release hormones. Here, they secrete what you call interleukins. That's the words that they do. See? So the phagocytes release this one, and this goes to the hypothalamus, which resets your thermostat in the the hypothalamus. You understand? And resetting the thermostat, bringing it, bumping it up a few degrees higher, so your temperature goes up. Don't you think that that's good? It will cook the bacteria, right? Don't we boil our water because we want to cook the bacteria, we want to kill them? I know you've taken up microbiology. What is it? We are called what? Mesophils, right? So if you increase, in other words, the bacteria that thrive in us, they like our normal body temperature. They live at that normal body temperature. You bump up the temperature, you change yourself to hyperthermia, it will kill the bacteria that's trying to survive in your body. That's the benefit, that's the advantage of fever. It also bumps up your metabolism. You want higher metabolism rate, right? Be Higher metabolism means more active. And as far as white blood cells, we want them to be more active. You boost their metabolism because you want them to be acting and killing the infection. The disadvantage is the rest, you go into fatigue. If you bump up your metabolism, all of your cells are going into overdrive. That's why you don't have energy when you're sick. Does it make sense? You're increasing the metabolism of every single cell in your body. You just lose energy. It's so we don't want the temperature to go up, 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 up. Besides, if you increase the temperature, you may run the risk of going into seizures. You know that. Nervous activity goes into overdrive also, you may go into seizures. So that's why low-grade fever is okay, but if it gets too high, you need to give Tylenol. So what type of protection is this one? Second line of defense. Okay? And I know you know about inflammation being a second line of defense, the benefit of inflammation. Okay? Now, at the same time, we call on our third line of defense. The third line is your last. This is your last defense, but it's your most effective type of defense. Are you understanding so far? You have your first line. Then when there's a breach, you have your soldiers right there, the second line. Your typical phagocytic cells. Then you have some proteins in there. Then you have fever, all trying to help. At the same time, they are calling on your third line of defense. And this is your last hope. But it's very, very effective. Now, why is it called third line of defense? Why is it very effective? What you need to know, write down in your notes, very important, okay? Your third line of defense are actually your T cells, the T cells and your B cells. These are your lymphocytes. So when there is a breach in your first line of defense, second line comes into play. You have your regular white blood cells, your phagocytic cells, right? Your phagocytes. And as the phagocytes are doing their job as they are trying to contain the infection, they are also actually calling this third line of defense. We're going to see how they call them. But this is the normal process. Do you understand this picture? First line is your skin, right? And the secretion. You have a breach. Second line comes into play, which are my regular soldiers. And also my proteins, my interferons, right? And my membrane attack, the complement system. But these phagocytes, they have a job of also, as they're trying to do their second line of defense, they're also calling on the third line of defense. We're going to see how they call. But I want you to know why this third line of defense, which is your lymphocytes, made up of your B cells and your T cells, why are they so effective? They are very effective because when they get called, so not only the B cell, I just only have a picture of the B cell here, but it's the same thing that happens with the T cells. So can you picture in your head, normally these B cells and T cells that we have, we start with the inactive form. They're just resting, right? My husband says, take easy. They're just always taking easy. So they're resting. When they get called, okay, these are your lymphocytes. When they get called, look at how they separate. They differentiate, they get activated, and they differentiate into two sets always. One is the active set, meaning the one actively fighting the infection now. Then the other set is what you call memory. They remember, they're on standby, so that in case you encounter the same infection next time, they know what to do. They're very specific. I target you. You remember this first line and second line? They're non-specific. They protect you the same way. Whether you're fighting bacteria, virus, whatever, they fight. Their method of fighting the infection is just the one and the same for everything. Whereas this one, they're very specific. And plus this memory. This is their advantage, the memory. This is why we immunize our patients, you see, or our children. The goal of immunization or vaccination is to have memory, so that in case you get sick, you don't have to wait for your body to make this. It already knows what to do. So that's why they say, do you remember? I'm sure you don't remember, but I just look at Lily. I remember her very, very first cold. Her very first cold, it was like horrible. And then, as you get older, look at you. I'm sure when you were babies, you had a terrible bout of maybe upper respiratory tract infection. But as you get older, because you have this one already in you, sometimes you just have a sniffles for 2 seconds and then it's gone. Because of this one. Do you understand, everybody? Do you understand this flow chart? Now I want to see how do lymphocytes call them. But you understand this one, everybody? No problem? Okay, break for 5 minutes, then we're going to talk about how they're getting called, okay?